You just spent $1,000 on a brand new processor, faster cores, more threads, a bigger number on the box. So why does your computer feel almost exactly the same as it did 3 years ago? Intel just laid off over 15,000 engineers. AMD's stock has been on a roller coaster for 18 months straight. And TSMC, the company that manufactures chips for almost every major brand on Earth, has quietly admitted that its most advanced process node is running 2 years behind schedule. This isn't a rumor, this isn't a leak. This is the current state of the industry building the most important technology on the planet. And yet, right now in 2026, you can walk into any store, spend over $1,000 on a brand new processor, and come home to discover your computer barely feels different than it did 3 years ago. Something is deeply fundamentally broken. And the biggest names in tech are hoping you never figure out exactly what it is. Here's the situation in 2026. Intel is fighting for survival after years of manufacturing delays, failed product launches, and an identity crisis that shook the entire semiconductor world. AMD has been riding high on its Zen architecture wins, but the gap between each new generation is getting smaller, not larger. Apple's M-series chips stunned the world when they launched, but even Apple is now hitting the same invisible ceiling that everyone else has been quietly crashing into for years. And Qualcomm, the company that was supposed to bring ARM computing to the Windows PC world and change everything, is shipping chips that are genuinely impressive in some benchmarks and genuinely disappointing in real-world use. Every single one of these companies is telling you the same story. New chip, faster performance, more cores, better efficiency, revolutionary architecture. But if you pull back and look at the actual numbers, not the benchmark numbers, not the cherry-picked demo numbers, the story the industry is telling and the story the data is telling are two very different things. The pace of real-world CPU performance improvement has slowed to a crawl, and in 2026, the reasons for that are more urgent, more complex, and more consequential than most people realize. Let's get into the real numbers, because the numbers are where the truth lives. In 2006, Intel's Core 2 Duo was a revelation. 2 years later, the original Core i7 nearly doubled real-world performance. 2 years after that, another significant leap. That cadence, that reliable doubling of capability, is what built the modern computing world. Fast forward to today. The difference between a high-end CPU from 2022 and a high-end CPU from 2026 in most everyday workloads, we're talking single-digit to low double-digit percentage improvements in many real-world tasks, not double, not revolutionary, incremental. The global semiconductor industry crossed the $600 billion revenue mark in 2025. It is projected to hit $1 trillion by 2030. The money flowing into chip development has never been larger. The engineering talent working on these problems has never been more concentrated. And yet the gains are shrinking. TSMC's 2 nanometer process, which was supposed to be in mass production by late 2025, faced yield challenges that pushed timelines. Intel's own 18A process, the one the company staked its entire manufacturing comeback on, has been watched by the entire industry with a combination of hope and skepticism. Meanwhile, the CHIPS Act poured tens of billions of dollars into rebuilding Western semiconductor manufacturing, and the plants being built right now won't be producing cutting-edge chips at full volume until the late 2020s at the earliest. The world is betting trillions of dollars on a technology that is running into walls it has never faced before. And in 2026, those walls are becoming impossible to ignore. In this video, I'm going to break down 5 specific, distinct, hidden problems that are quietly strangling the performance of every next-generation CPU on the market right now. Some of these are rooted in physics, some are rooted in economics, and number one is rooted in something that every person watching this video interacts with every single day without realizing it's silently working against them. Stay until number 1, because that's where the most important story in modern computing is hiding. And it's the one problem that no new chip announcement, no new process node, and no new architecture can fix on its own. Before we get into the list, here's the landscape you need to understand heading into 2026. The x86 architecture, the instruction set that has powered virtually every Windows and Linux PC for over 4 decades, is under serious competitive pressure for the first time in its history. ARM-based chips from Apple, Qualcomm, and now even Microsoft's own Silicon ambitions are proving that the old guard does not have a monopoly on performance. AI has completely reshaped what we expect from processors. In 2026, every major chip ships with a dedicated neural processing unit, an NPU, because AI inferencing workloads are now a standard part of everyday computing. Windows Copilot plus PC requirements, Apple Intelligence features, and on-device AI for productivity tools have all made NPU performance a genuine selling point. But here's the catch. Adding NPUs adds complexity. Complexity adds power draw. Power draw generates heat. And heat, as we'll see, is one of the core enemies of processor performance in this era. At the same time, the geopolitical dimension of chip manufacturing has never been more intense. Taiwan remains the epicenter of advanced chip production. And in 2026, that geographic concentration is not a theoretical risk. It is an active, daily concern for every government, every tech company, and every supply chain manager on the planet. The stakes of solving these hidden CPU problems are not just commercial. They are strategic, national, and civilizational. Now let's get into the 5 problems. Number 5, the memory wall, and why HBM isn't saving us. This problem has been lurking in the background of computing for 30 years, and in 2026, it's louder than ever. Here's the core issue. Processors have gotten dramatically faster at computing, but the memory they need to pull data from your system RAM has not kept pace, not even close. Think of it like this. Your CPU in 2026 is a Formula One car. It can complete a lap in under a minute, but the pit crew, your memory subsystem, still operates at roughly the same speed it did in 2010. Every time the car needs fresh tires, every time the processor needs new data, it has to slow down and wait. The numbers are stark. CPU compute performance has improved by roughly 3,000 times since the early 1990s. Memory bandwidth has improved by maybe 100 times in the same window. That gap, that yawning, widening gap between compute speed and memory speed, is called the memory wall. And every generation of processor runs headlong into it. The industry's answer in recent years has been high bandwidth memory, HBM. It's the ultra-fast memory stacked directly on top of or beside high-end chips, used extensively in AI accelerators and data center processors. HBM is genuinely fast, but it's also enormously expensive, physically complex to manufacture, and thermal to manage. You cannot simply slap HBM onto a mainstream consumer CPU and call the problem solved. For everyday users in 2026, this means that even on the fastest platforms, Intel Core Ultra, AMD Ryzen 9000 series, Qualcomm Snapdragon X Elite, your processor is still spending meaningful time idle, waiting for data that memory can't deliver fast enough. More processing power without matching memory bandwidth is like hiring 100 chefs for a kitchen with one refrigerator. Eventually, everyone is just standing around waiting. If you paid attention to the PC world in 2023 and 2024, you noticed something uncomfortable. Intel's flagship desktop processors, the 13th and 14th generation Core series, were drawing power numbers that left the entire industry stunned. Some configurations pulling close to 300 watts under sustained load. Laptop chips thermally throttling within seconds of hitting peak workloads. And then came the instability reports, a widespread issue affecting thousands of Intel CPUs that stemmed directly from the company pushing voltage and power limits far beyond what the silicon could reliably sustain. That was not a fluke, that was a symptom. The power wall, the fundamental physical limit on how much energy you can pump through a processor before heat destroys performance and reliability, has not gotten shorter as transistors have gotten smaller. In many ways, it has gotten taller. Here's why. Dennard's scaling, the beautiful physics principle that said smaller transistors use proportionally less power, collapsed in the mid-2000s. At nanometer scale transistor sizes, electrons leak. They tunnel through barriers they shouldn't cross. They generate heat even when the transistor is theoretically switched off. On a chip carrying 50 to 100 billion transistors, that leakage current adds up to a serious, unignorable thermal problem. In 2026, this is why flagship laptops with the most powerful processors still throttle aggressively under sustained load. Why desktop CPUs require 360mm liquid cooling solutions that cost as much as a budget PC. Why Apple has been so focused on performance per watt. Because in the mobile and laptop space, watt-efficient performance is the only performance that actually matters to real users. The processors being sold today are capable of extraordinary peak performance for short bursts. Sustained real-world performance under realistic conditions, that's a very different and much quieter story. IPC, instructions. Per clock. The metric almost no mainstream tech reviewer leads with, and the metric that arguably matters more than any other single number in processor performance. Clock speed tells you how many cycles per second a chip runs. IPC tells you how much useful work gets done in each cycle. A chip running at 3.5 gigahertz with high IPC will absolutely destroy a chip running at 5 gigahertz with low IPC in real-world tasks. The clock speed number on the box tells you almost nothing without the IPC number behind it. For decades, IPC improvements drove enormous performance gains even when clock speed stagnated. Superscalar execution, out-of-order processing, branch prediction, speculative execution. These architectural innovations stacked on top of each other and let chip designers squeeze dramatically more work out of every clock cycle. But in 2026, those gains have mostly been harvested. The low-hanging fruit of microarchitectural optimization was picked years ago. What remains is a harder climb for smaller rewards. AMD's Zen 5 architecture, released in 2024, delivered IPC improvements in the range of 10 to 16% over Zen 4. Meaningful, absolutely. But a decade ago, a new architecture generation could deliver 20 to 40% IPC improvements. The trajectory is undeniably flattening. And there's a security dimension here that the industry has never fully reckoned with. Spectre and Meltdown, the devastating hardware vulnerabilities disclosed in 2018, were direct consequences of speculative execution, one of the primary IPC boosting techniques. Mitigations have been applied, but those mitigations carry performance penalties that, in specific workloads, are still felt today. The architecture that made chips fast also made them vulnerable, and unwinding that relationship is enormously complex. The IPC plateau is not a cliff, it's a slow, grinding deceleration. But when you track it across multiple generations, the direction is unmistakable. If you follow processor news in 2026, you've heard the word chiplet constantly. AMD pioneered the aggressive use of chiplet-based design with its Ryzen and EPYC processors. Intel followed with its Foveros 3D stacking technology. Apple has been doing something similar with its die-to-die interconnects and M-series chips. The idea is smart. Instead of manufacturing one giant complex piece of silicon, which has lower yield rates because a single defect anywhere on the die kills the entire chip, you manufacture multiple smaller, simpler dies and connect them together. Better yields, lower cost per unit, more flexibility in mixing different process nodes for different functions. The concept is brilliant. The execution is incredibly hard. Because here's the thing about connecting chiplets. Connecting them introduces latency that does not exist on a monolithic design. Data traveling from one chiplet to another takes longer than data traveling between components on the same die. And while engineers have become remarkably clever at minimizing this latency, AMD's Infinity Fabric, Intel's EMIB interconnect, it cannot be reduced to zero. Physics won't allow it. In 2026, we're seeing the downstream effects of this complexity. AMD's high-end Ryzen 9000 series with 3D V-cache, where a cache chiplet is literally stacked on top of the compute die, delivers extraordinary gaming performance because it slashes the latency of accessing frequently used game data. But it also runs hotter and creates thermal management challenges that the previous generation didn't have. High core count workstation and server processors with many chiplets show measurable NUMA, non-uniform memory access, effects where tasks running on cores in one chiplet are penalized relative to tasks running on cores closer to the memory controller. The chiplet era has genuinely extended what's possible in semiconductor design, but it has also introduced a new category of complexity tax, hidden performance penalties that don't show up in headline benchmarks but absolutely show up in real-world workloads. This is the one nobody in the industry wants to talk about, because it's not a hardware problem. It can't be solved with a better fab process or a smarter microarchitecture or a $1 billion R&D budget. And it is, right now in 2026, the single biggest reason that the average person's computing experience has not improved proportionally to the hardware improvements of the last decade. It's software. Specifically, it's the catastrophic accumulation of software debt. Here's what has happened. Over the last 15 years, the economics of software development changed completely. The rise of cloud computing, subscription software models, agile development cycles, and JavaScript-based cross-platform frameworks created enormous incentives to ship fast and iterate constantly. The incentive to deeply optimize software, to rewrite it for new hardware architectures, to strip away bloat, to take advantage of modern CPU features, largely disappeared. The result is that in 2026, vast swaths of the software ecosystem are running on code bases that were fundamentally structured in the 2010s or earlier. They are running on abstraction layer on top of abstraction layer. An Electron-based desktop app, for example, and there are hundreds of major, widely used Electron apps, is essentially a web browser running a website pretending to be a native application. That means Chrome's rendering engine, Node.js, JavaScript, and the operating system's own abstraction layers all standing between your code and your processor. Every one of those layers is a performance tax, and those taxes compound. There is an observation in computing sometimes called Wirth's law. Software grows slower faster than hardware grows faster. In 2026, with AI-generated code shipping at volumes that were inconceivable 3 years ago, this problem is accelerating. Developers using AI coding assistants can produce more code faster than ever. But more code, produced faster, with less deep architectural review, means more bloat, more inefficiency, more abstraction. Meanwhile, the shift to ARM on Windows, driven by Qualcomm's Snapdragon X chips and Microsoft's own silicon ambitions, has exposed just how dependent the software ecosystem is on x86. Emulation layers that translate x86 instructions to ARM instructions work surprisingly well. But Surprisingly well and optimally fast are not the same thing. In 2026, many Windows applications running on ARM platforms are still running through emulation, leaving significant performance on the table. Apple solved this problem for its platform with Rosetta 2, and then by driving developers to native ARM builds over a multi-year transition. Microsoft is attempting the same, but Microsoft's ecosystem is vastly larger, vastly more fragmented, and vastly harder to coordinate. The hardware engineers are building extraordinary machines. The software ecosystem is a 30-year-old city built for different streets, trying to accommodate traffic that has multiplied 1,000 times. That is the number one hidden problem with next-generation CPUs in 2026, and it cannot be solved by any chip announcement you will see this year. Here's a bonus problem that is going to define the next 5 years of computing in ways nobody has fully reckoned with yet: the AI workload mismatch. In 2026, every major chip ships with an NPU, a neural processing unit, specifically designed to run AI inferencing workloads locally on your device. Windows Copilot Plus requirements, Apple Intelligence, Snapdragon's on-device AI features. All of this depends on NPUs hitting specific performance thresholds. But here's the problem nobody's clearly articulating. The AI models being deployed in 2026 are growing faster than the NPUs designed to run them. The models that fit neatly on a 45 TOPS NPU 6 months ago are being replaced by models that require 60, 80, 100 TOPS to run at acceptable speeds. The goalposts are moving faster than the silicon. This creates a situation where the on-device AI features being marketed as reasons to buy a new chip today may be inadequate for the AI workloads of 2027. Not because the chip was poorly designed, but because AI development has an entirely different velocity from chip development. The chip industry operates on 2 to 4 year design cycles. AI model development operates on 6 to 12-month cycles. Those two timelines are violently mismatched. And the consumer in the middle is going to feel that mismatch very concretely in the next few years. Here's the pushback I know is coming. You're going to say, look, benchmarks still show improvement. New chips are still faster. If things are this bad, why do reviewers keep recommending upgrades? Fair. Completely fair. Let's address it honestly. Yes, new chips are faster than old chips. The improvements are real and measurable. If you're on a processor from 2018 or earlier, a modern chip is a genuine, noticeable upgrade in many workloads. Nobody is disputing that. What's being disputed is the narrative that each new generation represents a meaningful leap rather than a marginal step. In 2026, if you own a processor from 2022, the honest advice from the data, not from the marketing, is that upgrading to a 2025 or 2026 chip will deliver perhaps 10 to 20% better performance in most everyday tasks. For that, you're often looking at a new motherboard, new RAM, potentially a new cooler, and several $100s. That value proposition is very different from what it was a decade ago. And there's a deeper issue with benchmarks specifically. Most benchmarks are synthetic, designed to stress specific components under artificial conditions. They are optimized to show what hardware can do at its theoretical peak. Real-world computing rarely looks like a benchmark. Real-world computing looks like 30 browser tabs, a Slack window, a Spotify stream, and a video conference, all fighting for resources simultaneously. For those workloads, the gap between chip generations looks very different than it does in a controlled benchmark suite. The chips are getting better, but better at what, by how much, and for whom? Those questions deserve much more rigorous answers than the industry tends to offer. Let's bring it home. If you're a gamer in 2026, unless you're on hardware older than 2019, the CPU is almost certainly not your performance bottleneck. Your GPU, your RAM speed, and your game zone optimization are far more likely culprits. If you're a creative professional doing video editing, motion graphics, or 3D rendering, platform matters more than generation. Switching ecosystems, particularly to Apple Silicon if you're not already there, may deliver more real-world improvement than staying in x86 and upgrading generation to generation. If you're a developer or AI researcher, the memory bandwidth and unified memory architecture of your platform may matter more than raw core count. And NPU performance is going to matter increasingly for local AI workloads over the next 18 months. If you're tracking the future of computing, the 5 hidden problems we covered today are the defining story of this industry right now. The memory wall, the power wall, the IPC plateau, the chiplet complexity tax, and the software debt catastrophe. These are the forces every chip designer, every software architect, and every technology policymaker is wrestling with in 2026. There's a version of the future where these problems get solved, where new memory architectures, processing and memory designs, where computation happens inside the memory itself, eliminate the memory wall, where 3D chip stacking matures to the point where chiplet latency becomes negligible, where the software industry, pushed by competitive pressure and the demands of AI, undergoes a genuine re-architecting effort that eliminates decades of accumulated bloat. That future is not fantasy. The research exists. The prototypes exist. The people working on these problems are among the most brilliant engineers alive. But here's the thing. That future is not delivered by a product announcement. It is not delivered by a marketing slide that says revolutionary. It is delivered by solving hard physics problems, hard economics problems, and hard human coordination problems simultaneously over years and decades. We are in the uncomfortable middle part of that story, the era where the old roadmap has clearly run out of road, but the new roadmap is still being drawn, where the chips getting released today are genuinely impressive achievements, and simultaneously genuinely inadequate for the scale of what the next decade of technology demands. The question isn't whether the next processor will be faster than the last one. It will be. The question is whether fast enough and soon enough will be enough for a world that is about to demand more from computing than computing has ever been asked to deliver. That is the hidden problem with next-gen CPUs. And in 2026, it has never mattered more. So here's my question for you. Out of the 5 hidden problems we covered today, the memory wall, the power wall, the IPC plateau, the chiplet complexity tax, and the software debt catastrophe, which one do you think will get solved first? And which one do you think we're still talking about in 2035? Drop your answer in the comments. I read every single one, and the best takes might just make it into a future video. If this video gave you a clearer picture of what's actually happening inside the chips powering your life, share it with one person who's about to spend money on a CPU upgrade. They'll thank you for it. Subscribe if you want the real story of technology, not the press release version. See you in the next one.